we're actually going to do something a little more explodey. I'm going to have you crush the light bulb with these pliers. What do you think is going to happen when you crush this light bulb?
Are you sure this is safe?
Yeah. Hey guys, welcome to another episode of Tinkering with Tiny Humans. We have both of my tiny humans today, Jacob and Lainey, and we want to give a shout out to Miss Cheryl Zenko's students in Rocky River, Ohio, and we're going to give you a lesson on the type of circuits today, and we look forward to it. So every time we do a video, Lainey always brings some friends to it, and she is enamored with Hamilton right now. So she has created Lego minifigures that are representations of each of some of the main Hamilton characters. So can you tell us about it, Lainey?
I have the king.
Yep, he's a fun one.
I have Eliza. I have Burr. I have George Washington. And I have Angelica, yeah.
Angelica, yeah.
And Hamilton.
And that's it. Who's that, Eliza?
Yeah.
Oh, very cool. All right, so we'll put those over here. Today we're going to talk about the two main kind of circuits that are in existence in the world, and those are series and parallel circuits. Now, in every circuit, there has to be a flow of electrons, and technically the electrons don't flow in a circuit, but it's how we think about it, because it's just a helpful tool to help us visualize stuff. So here we have a simple circuit, and in every circuit, there's pretty much a relationship between voltage, current, and resistance. And that relationship is something that we can figure out mathematically. And sometimes people use the analogy of a garden hose to describe those three variables: voltage, current, and resistance. So on a garden hose, the amount of pressure of the water is what we equate to voltage. And voltage is the potential for energy to move. So on a 9-volt battery, that has a certain amount of voltage associated with it, 9 volts. Your outlet in the wall of your house has either 120 or 100 and 240 volts. So some of your big appliances use 240 volts, your smaller stuff uses 110 volts, and voltage is the potential of energy to move. Current is the flow of energy in the circuit. We call those amps. Amps would be the equivalent of how big of a diameter hose you have. So if you have a garden hose, that would be a small number of amps. If you have a fire hose, that would be a large number of amps. And finally, sometime when you step on a hose and you restrict it, or if you kink it, it creates a restriction, and that is resistance. So in every circuit, there is going to be some amount of voltage, current, and resistance. And on this circuit right here, we have a partial circuit, because we have an open end here, we have an open end here, and we're just going to think about it in a big loop. And we can't have a circuit unless the loop is completed. So this is an example of a series circuit, and then we'll show you an example of a parallel circuit. And in a series circuit, that means that there's only one loop for the electricity to flow through. So Jake, if you could take the power supply and attach one side of the alligator clips to here, and Lainey will attach the other side of the alligator clips to here, we will... Yeah, they do look like dragons, don't they?
No, Min-Min's arms got tangled.
All right, hook it up.
It's a weird animation.
So there's a little notch here, look. There's a little notch in the front, so just stick it in the jaws and go, yep. There you go. So again, in our garden hose analogy, we'll put up a little graphic. Voltage is the water pressure. Current, or amperage, is the diameter or the thickness of the hose. And resistance is someone stepping on the hose or kinking it. And that's what we have set up right here. We now have a complete circuit. We've got a power supply. That power supply could be a battery, but this one just lets us set the voltage to whatever we want. And we've got a path going here. Then it goes to a resistive load, which is a light bulb. And then it goes to another resistive load, which is a light bulb. And then to another resistive load that's a light bulb. And then to the other side of the power supply. All right, Jake and Lainey connected up the power supply. And there's a weird thing that we kind of have different ways of talking about. When we talk about positive and negative, we say that the current flows from the positive to the negative, but the electrons internally of the circuit actually go the opposite way. But we're just going to talk about it as if the current is going to go from our power supply, from our positive lead, into our one resistive load, which is a light bulb, down the other conductor into the other resistive load that's a light bulb, down the other conductor into the third resistive load that's a light bulb, and then returning back to the power supply. So if we start to increase the voltage,
Infinite power?
these bulbs are supposed to be at their proper brightness at 14 volts.
Oh, they're
So
lighting up.
I'm going to turn this up to 14 volts and we're going to observe something.
They look like Christmas lights?
They do look like Christmas lights, but they are not very bright. So what do you think might be an explanation for why they're supposed to be at full brightness at 14 volts, but they're not really all that bright? Any thoughts?
Because it needs to be distributed between all the three.
That is an excellent observation, and that is correct. Because in a series circuit, the voltage across each bulb is not the same as what is supplied to the circuit. So I'd like you to do some testing for me. This is a multimeter, and this will help us test voltage at different parts of the system. So I can tell you with certainty that this power supply is correct, but yeah, you can test something. We have this on DC volts. I'd like you to take one of each of these clips and just kind of touch it to the supply of the power supply, the input of the power supply. So you see how like when you squeeze this clip, these little spiky things come out? So squeeze those out and touch them inside there, and let's look what the meter says. All right, so the meter says, you had it there? Yes, the meter says 14.0 plus or minus volts. So that means the power supply is reading the correct value, but these bulbs are pretty dull. So here's an interesting thing. We think they're distributed about evenly. So let's use some estimation skills. If we say instead of 14 volts, this is 15 volts. If we did 15 and we divided it equally amongst 3 light bulbs, how much volts would you say is across each light bulb?
45. Wait, no.
What?
No, she multiplied instead of divided. What do you think, Jake?
Wait, I didn't hear the question.
We've got 15 volts and it's split evenly among these 3 bulbs. How many volts would
5.
you think? 5 volts? Yeah? What do you think, Lainey?
Yeah.
So I think you tested that. So Lainey's gonna do a test here. I want you to put one terminal to the left of the bulb. See there's like a little bare spot on the wire? You see how when you squeeze this, the little claw comes out? So yeah, attach the claw to there and attach the claw to there. And I think what we're gonna find is a number around 5 volts. You can do them separately, it's okay.
It's possible.
We have 4.5 volts. And since we estimated, that probably is exactly correct because 4.6 times 3 is going to get us very close to 14 volts. So this is 4.6 volts. And this is, I can't see the hooky dookie, 4.6 volts. And this is 4.6 volts.
Sad.
No matter what we do, if we supply 14 volts into a series circuit, we will not see 14 volts at each of the loads. They're going to be distributed proportional to their amount of resistance. And since we have the same amount of resistance on each of these bulbs, for our purposes, they're divided evenly.
Are we going to turn it up to 45?
Well, we could do that. We can increase the voltage, and your guesstimation is correct. If we want to see about 16 or 14 volts on each light bulb, we can turn it up to 42 volts because that's the most that the power supply, no, 25 volts is the most the power supply will go up to.
25?
Yeah, we can get up to 25. So we got 25 volts going into the system, and if we take 25 divided by 3, 25 divided by 3, we get 8.3 volts. Let's double check it. Jake, put this on one side of that wire and this on the other side of the wire, and let's see if we get 8.3 volts. 8.8 volts, so there's some variability here, but yeah, they're basically split evenly amongst the 25 volts that we gave it. So that's pretty cool. So this is a series circuit. That means there's only one way the voltage goes in and out, only one way for the current to go in and out. And on a circuit like this, if you were to cut or break one of those light bulbs, it would kill the electricity everywhere. And we'll do that test in a little bit, okay?
We're gonna cut one of the light bulbs?
Yeah, we're gonna cut one of the light bulbs.
I'm scared.
Don't be afraid. Okay, so that was our series circuit. On a series circuit, that means the current is the same everywhere in the circuit, but the voltage is different across each of the loads. All right, circuit number 2, this is a parallel circuit right here. So in a parallel circuit, it's almost like a ladder. See this like ladder shape?
Yeah.
So the power is applied to it, and it goes to this bulb, but this bulb is also connected in parallel to this bulb, and this bulb is always connected in parallel to this bulb. So let's hook up our power. Oh, you know what? I forgot to mention something. This is important. So this circuit right here, when we had it on 14 volts, it only used maybe 0.2 amps, I think. Let's double check. So at 14 volts, it used 1.8 amps. So we're going to compare that to our parallel circuit. All right, Jake, hook us up.
Oh!
So this end right here is open, right? And we talked about you can't have an open circuit and have electricity flow. So why is this working? Any idea?
Because this is also connected to this.
So follow it with your finger. How's the electricity going?
So wait, it comes out of here.
Yep.
It splits up here. And breaks.
So these are like a bunch of loops. Watch. I've got a loop here. I've got a loop here. And I got a third loop here. So these are all in parallel with each other, which means they're like multiple independent circuits. So we talked about it only needed 1.8 amps to operate the circuit at 14 volts last time. Right now, the screen is telling me it's using 1.3 amps. So that's roughly 5 or 6 times more current than before. So in this type of circuit, in a parallel circuit, every device sees the same amount of voltage that you put into it. But what happens is the current is different. So the current from here and the current in here and the current in here are all different. So let's test it. Remember on the other one with our dim bulbs, they were only 4.6 or 4.8 volts. Why don't you connect this up across the light bulb and see what you see?
Wait, where do I connect it?
Those little like bare spots there and there.
Does it matter like...
The polarity doesn't matter. It'll just read negative on the meter. It's not a big deal. I think your other one is not connected. You got to put one on here and one on there. 14.05 volts across this light bulb. And this one's also, I'm going to say, you want to connect this one up, Lainey? Yeah, you can connect up to that one. Yeah, okay. There we go. 14.03 volts. So in a parallel circuit, every device sees the same voltage, but the current is not the same through each of these loops. And the current is much higher than it was in the shared circuit that was in series. So they're kind of like as a compromise. So we know these two kind of circuits. This one has a different voltage across each device. This one has the same voltage across each device, but more current. What do you think your house is wired up with? And how would you explain how you decided that? So like the outlet in our house, there's one right there, there's one right there, there's one right there. Do you think those are hooked up in series or in parallel?
I think parallel.
Tell me why.
Because for the LEDs, like the light's kind of in the middle.
Yeah.
You can dim it easier than like that would be harder to dim.
Here's a
I'd
hint.
say,
Here's a hint. And I don't know if I told you this. So your laptop, when you plug it in, or your iPad charger, when you plug it in, it wants to see 120 volts all the time. It can tolerate some variations, but it really wants to see 120 volts every time. So which of these two circuits will give you the same voltage across each one of these? Yeah, parallel.
I would say this one because like the outlets are stacked on top of each other.
Yeah, that is kind of like a visual clue for them being connected together. So yes, inside of each duplex outlet, those are wired in parallel, and those outlets are wired in parallel to the outlets down the room from it. So yes, in a house, almost everything is done in parallel. And there's a third type of circuit that we have that's called a combination circuit. So we're going to put both parallel and series together, and we're going to show you how they behave differently. So Lainey and Jake, can you twist one end of this together, and the other person twist that end together? We'll turn off the power. It's not going to hurt you, but I just don't want it shorting out. All right, now that we have tied everything together, these are very, very dim.
Yeah.
These ones are still just about as bright because what's happening is there is 10 volts. What's that?
Just the lights, the energy is still being split evenly, but it's less for these because it...
No, it's because the ones that are still in parallel are seeing 10, the most that I can get right now is 10.3 volts because it exceeds the amperage of the power supply. So the most I can give is 10 volts. This is seeing 10 volts, this is seeing 10 volts, this is seeing 10 volts. And what do you think happens right here?
It sees 5 volts.
Less volts.
It does see less volts. What does it see?
It sees
What,
33.33333333 volts.
3.33333 because you've taken 10 volts and you divided it by 3.
Oh, yeah.
So this one has 10, this has 10, this has 10, and this whole thing has 10, which means if I test this, I bet it is going to say 3.3 volts. 3.3 volts. How about that? Pretty cool. Another difference between parallel and series is that in a parallel circuit, if you remove one of the devices, everything else still works. So in your house, if you unplug one outlet, all the other outlets still work. In a series circuit, if you remove one of the devices, it kills the flow of electricity. So let's check this out. Lainey, I want you to make a hypothesis. What's going to happen if you cut this wire right here with these wire cutters? What do you think is going to happen? Don't do it yet.
Bet.
What's your hypothesis? Hypothesis means an educated scientific guess.
I bet
Yep.
that they're all gonna flow out.
They're all going to flow
Get
out?
out.
So follow what happens to the voltage or the what happens to the continuity of the circuit when you cut this. Where is it going to go in?
Actually, I bet these ones would stay.
Those ones will stay?
I think that they're all just gonna go out.
All of them?
I think some will stay.
Which ones do you think will stay?
I think that
Like
these
maybe
ones will
this
stay.
one will go out, and then like these ones will stay since they have their own power.
So you think this one will go out? That's Lainey's hypothesis, right? And Jake, what do you think is going to happen?
These ones will stay. Those ones will go out.
Interesting. Why do you think that?
Like you said, if the power's cut off, then everything stops. But if you cut, I bet that if you cut like
yeah.
one wire here and then one wire here, it would still go out.
Okay. So
These ones
Now
still
that
go
I
out
think
that
about
way.
it, they don't get power from both sides. They only get one side and they pass it to the other.
okay. So is your theory still only this one's going to go out or something else?
Oh, I think that if I cut it here,
Yep.
this one will go out.
Okay. Okay. Let's do it.
The moment of truth. Cut already.
Oh, you're on the stripping part. You got to like put it there. There you go. Squeeze. All right. So let's see here what happened.
That's correct.
This one out, and this one out, and these stay together because in a parallel circuit that we've attached a series circuit to, we've broken the series circuit, but we have not broken the parallel circuit.
Wait, does
cut
that
the
mean?
parallel
Wait,
one.
can I try this?
No, I want to try something else. So,
If you cut this, it'll probably all stay on.
well, we're actually gonna do something a little more explodey. I'm gonna have you crush the light bulb
Please don't, please.
with these pliers, and I want you to tell me what do you think is gonna happen when you crush this light
There will
bulb?
be glass everywhere.
Are they
Yes.
all gonna go out, or are they gonna stay on?
They're gonna stay on
How come?
because they're
I
all.
still think this glass
They're not
one is
feeding power. They're not like feeding power through a circuit. They're just. I
You
think.
think these two will go out?
I don't think that
Yes.
they're all gonna go out. That's just my
Okay.
hypothesis.
Okay. Give it a squeeze.
Are you sure this is safe?
Yeah.
Is this legal?
No,
Oh my goodness.
they all stayed on.
So in a parallel circuit, when one of the devices is removed or destroyed, the other ones still work. Pretty cool. Well, what happened was when these are in a vacuum, so when they make these at the factory, all the air is sucked out of this. So when you crush the glass, it let oxygen in, and that caused this to burn a little bit. But it's dead. Whoops. So our series circuit, if one goes out, they all go out. And our parallel circuit, that is not the case. Now here's a wacky thing. Christmas lights. You think Christmas lights are in parallel or series?
Series.
How come?
Wait, these ones are these
Par-
series? No, these
Yeah.
are parallel.
Those
sorry,
are parallel.
Parallel.
Why do you say that?
Because
They have like two wires, and like sometimes wait.
like a Christmas light, if there's a dead one, not all of them go out. And if you remove it, still not all of them go out.
Interesting. What do you think, Jake?
That's why I think it's
Yeah, I thought that like. Yeah, same thing as Lainey, because like they don't like all go out.
So here's an interesting thing. Christmas lights are in series, almost all of them made in the last 50 years. And yes, they're this kind, where one of them goes out, they all go out, but there's a trick that they do to make that not happen. So if you actually unplug one bulb from Christmas lights, they all go out. But if one of them burns out, there's a special winding inside there. Yes, every group of 100 is connected together. So in Christmas tree lights, each of those bulbs is supposed to get 1.2 volts. Why do you think those bulbs are supposed to get 1.2 volts if there's 100 of them?
If there's
probably
1.2 because there
Okay.
is like 120.
That is excellent. Wall voltage is 120 volts. So if you have wall voltage at 120 volts and each bulb out of 100 shares 1.2 volts, everything is perfect. So those are all done in series because in our experiment, we saw that a parallel circuit requires a lot heavier wire because it needs to be able to handle more current, more amperage. And if you were to wire together 100 light bulbs in parallel on your Christmas tree, it would need cables that are like this thick, and that'd be really a pain and really expensive. So the trick is they use really skinny wires, they put them in series, but there's a special winding inside the bulb so that if the bulb burns out, it still keeps the electricity going. Pretty neat, huh? Cool.
Wait,
all right.
I told you they look like Christmas lights.
They do look like Christmas lights, yes.
Yeah, but like, if you like took one of the lights out, wouldn't it still be going because of the wire on the inside?
If you unplug one bulb from a Christmas tree light set, all 100 bulbs will go out. Yeah.
It's very...
Yeah, it's true. Or if you accidentally step on one. That's why they're really hard. If you're like setting up the tree and you step on one and crush the bulb, they're really hard to find which one has went out. Yep. So today we learned about 3 different circuit types. Well, 2 circuit types and 1 hybrid. We learned about the parallel circuit, where it looks like a ladder and every device sees the same voltage, but there's different currents. And we've talked about the series circuit, where the current or amperage is the same everywhere, but each device has a different voltage drop across it. And we talked about the hybrid, which is a combination of both both parallel and series circuits. And we tested each one of those. Combination circuit. We really appreciated sharing that with you today. And if you have any questions about that, we would love to hear about it in the comments below. And if you enjoyed this, please like and subscribe because we'd like to make some more videos for you. And lastly, we would love to hear your suggestions. If there's anything you'd like us to try or anything you'd like an explanation about, we would like to tinker and figure it out and share our learning with you. So thank you so much for joining us. Have a great day. Bye.